All right, welcome back to Introduction to ComputerNet. Hey, today we have nothing new to say from the announcement, so we'll go ahead and start with topics today. And starting today, we'll talk about the first application called the web transfer. And as you can see from the topics, HTTP is the application layer protocol supporting web transfer. All right. So the first video is just to give you all the basic terms and basic components. There will be 3 parts. First part, we'll talk about URL. Okay, we all know about URL, but there are 3 components. Okay, when you are writing a URL, make sure that you present all 3 components. Second part, you will see. Recall yesterday and last week, we talked about when you're designing a network app, you want to think about what is the architecture communication model, right? So web transfer is the first application that we'll look into the detail. Think about, okay, for HTTP, there must be some sort of communication model the designer of HTTP defines. So is it peer-to-peer or client-server based? So in the second part, you'll see. The third part is, hey, next thing, after considering the architecture, we design the socket. We start a socket, okay? And what's critical starting a socket is, hey, what is the underlying transport layer protocol used? In the third part, you will see in HTTP, we use TCP, all right? So having 3 parts, this video is a little bit long, 5 minutes and 40 seconds. Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are 3 parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now, another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there, is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server, very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think is still the most used server, but this guy here is catching up, Nginx. Both of these servers are implemented using C and C++ socket, all right? So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP requests and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, yeah, Safari sending HTTP request, and server sends back an object, and Safari renders and displays the object. All right, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new, it's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. All right. Yeah, protocols that maintain states can be complex. So this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right? All right, so that's the basics of HTTP and pretty much all of HTTP. And in that past video, make sure that you pick up this. HTTP is stateless, just to keep things simple and scalable. Now, next, we're going to talk about how HTTP manages the TCP connection. I mean, HTTP socket is TCP, and it seems that we start the TCP and that's it. In fact, how each of these clients manage the TCP connection, each of the client-server pair manages the TCP connection can vary. Okay, over the years, HTTP has sort of gradually improved how they manage the TCP connection. And there are three modes typically an HTTP client-server pair use. So that's what the next video is about. And this one is about 4.5 minutes. HTTP connections. There are actually three flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. All right, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request and the object response exchange, and so on and so forth. So one single connection to send all the objects, all right? Now, the basic persistent HTTP mode works more like this. So you have one exchange to establish TCP connection. And then it's just object 1, and object 2, and then object 3. Okay. But the thing is this. When we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object will wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a sure, open it message. Second exchange is the client sending the request message. All right, so in the message, embedded is the URL. All right, so that's going to go through the socket, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. All right, so you see there are 3 modes, right? It has something to do with after we start the TCP connection, whether we keep it for later use or not. And after we know that there are several objects and we already know the URLs of these objects, maybe we can send the request back to back in case these objects are all on the same server. So how the 3 modes vary. And what you're seeing there in the later part of the video is the exact exchanges of messages. And you see also the time it takes, right, to complete a non-persistent connection HTTP exchange. You know what? As I mentioned in the video also, that the reason that we have these different modes of a connection is because over the time, we find that we can probably save time downloading these objects quicker if we better manage the TCP connection, if we better manage how we send the requests when the URLs are available. So you can sense already, right? The key metric, in evaluating whether HTTP protocol is working well or badly is what? The time it takes to download the whole page. And that is called the response time. So in the next video, Polly will define response time. And you will see an example of how long it takes to download objects using a non-persistent HTTP connection versus persistent with pipelining HTTP connection. Okay, and right after this video, we'll exercise, okay, whether you know how to calculate response time in quiz 9. So pay attention to this one. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server code over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's one round trip time, right? So one round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is one round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So let me fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just one object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX, okay, and depending on which object it is for OI. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, it's just one round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version. All right. So let's exercise and see if you get the idea. Okay. So this is quiz 9, and let's go to the whiteboard mode. There we go. Okay. So quiz 9. Can you tell the time to download the web page? But this time, unlike the example we used in the video, we have 1 base HTML and 5 reference objects. So once again, okay, good morning, sparrows. Once again, the base HTML needs to be downloaded first, then you know the URLs of the 5 reference objects. So you cannot be downloading all 6 objects at once, okay, immediately, okay? So 1 base, yeah, you get this, and then you see, there are 5 more reference objects you need to download in order to render the entire page, Okay, good. And for the sake of simplicity, clarity, let's ignore the transmission time. Let's just ignore, negligible, okay, transmission time relative to the round trip time. Now, Q1 asks, hey, what is the time to download this page if we use non-persistent HTTP? So this will be the version 0.9, right? HTTP 0.9. And for 1.1, okay, what is the time? And Q3 asks, right? We said that there are 3 modes. So the third mode is actually persistent HTTP without pipelining. This is actually the version used by HTTP 1.0. Okay, and this is without pipelining. That means you cannot manage the requests of the objects flexibly. Okay, essentially we'll need to ask for the objects one by one. After we get the first one, close the TCP connection. Get the first one, then we start asking for the second one. Good. And 4. Okay, so this is new. Polly did not talk about it in the video. How about using non-persistent HTTP? Okay, but we are allowed to create 5 parallel connections maximum simultaneously. What you can do is then in Q4, you can download the base HTML, and for the 5 reference objects, hey, how about starting 5 parallel TCP connections and 1 for each object? Okay, that's doable in Q4. All right, guys, think about it. Let's go to the Discord space. You will see quiz night is already here. Okay, so the example now is 1 base and 5 reference objects. And for this one, guys, let me challenge you a little bit. You guys have only 3 minutes, okay, to answer all 4 questions. And let's start counting time. right, time's up. Hey guys, how are you? How are we doing? Okay, yeah, this one is probably interesting and exciting. All right. And Ellen, you're the first. Great. Okay, appreciate being able to open about what you think the answer is. Okay, and we see that Ellen says 12 RTT for Q1, and it's very clear, right? So he's showing the entire formulation. So one round trip time for establishing the TCP connection, one round trip time to send to get the base HTML. Great. And you know what? This is gonna be for the base object as well as all the rest of the 5 objects. So essentially, how many objects you have multiplied by 2 RTT. Okay. So that will be 12. Okay. I think we get this, no problem. Okay, if you follow the video. For the second one, yeah, we have one round trip time for the base object, right? But we keep the connection in persistent mode, and we can fetch all the 5 objects at once in one round trip time. So the delay is always the round trip time, no matter how many objects there are, isn't it? If we ignore the transmission time. Perfect. And Q3 is the thermal. It's kind of in between, right? We keep the TCP. That's not close it. Okay. But we request the objects one by one. Okay. Wait until the second object has arrived, then we get the third one. Okay, so we would have one round trip time to collect the base. But for each of the 5 objects, we will need one round trip time, right? So that will be 7. Perfect. Last one is tricky because you guys did not see an example of this, all right? So we would have one round trip time. You see here? Here's the, oh, okay, hey, I see Ellen modify this. Okay. Yeah, and if this is non-persistent HTTP, Ellen, I think the key point is non-persistent. Okay, if it's persistent, then of course, you're going the right direction. But you're probably missing this. Non-persistent HTTP, once you get the base object, right, you close the TCP connection. And for the rest of these reference objects, you would definitely need to start a TCP connection altogether. Okay, so that's definitely another round trip time already. In case this is non-persistent HTTP with parallel connections. And since that we can have 5 parallel connections at once, so for 5 reference objects, we just get them in 2 round trip times. A HTTP connection established first, and then get the individual reference objects from individual parallel connections. All right, good, Alan. I hope it's more clear what non-persistent HTTP with 5 parallel connections meant. Oh, and you can see from Katie's solution here. All right, good. 2 round trip time for each single object. So yeah, you know now very clearly. In the non-persistent HTTP, okay, the answer is always 2 round trip times multiply the number of objects. Q2, it's always 3 RTTs, isn't it? But this is, of course, assuming that all the reference objects are on the same server as the base object. Okay, for Q2, if Polly sort of changed the problem a little bit, in case the reference objects are on another server, what would the answer be, right? Then it's a little bit different. Good. Q3, we know. Yeah, it's 2 round trip time to get the base, and then 5 objects, each would take 1 round trip time, definitely. So 2 RTT, the base, and 5 RTTs for each of the reference objects. First object takes 2 round trip time, and the remaining 5 objects can be sent in parallel. Perfect. Okay, so guys, we have a reference solution here. Okay, excellent. Let's see. All right, 12, slightly more than 3. May have some delay. Yeah, so, well, in this case, we are kind of ignoring the transmission delays and, of course, the other minor delays. Okay. And 7 and 4. Very good. 12, 3. Okay. Lloyd is very concise here. Okay, so you know that there are 6 objects, each 2 round trip time. This is 1 round trip time, 1 round trip time. So you kind of skip the unit of it. Yeah, so 1 round trip time for the connection establishment, 1 round trip time to get the base, and 1 round trip time to get all 5 reference objects. Very good. Jordan, there you go. Okay, you guys have different way of expressing what you meant numerically, okay, arithmetically, okay. All right. Very good. Guys, if you are aware, right, then you can compare in this particular example, which mode of communication is the most efficient, isn't it? And which one is it? Still the persistent connection, the persistent mode, isn't it? In the parallel connection mode, you see that there's a cost of doing it, because to start parallel connections, for each connection, it will require the computer to allocate some memory to manage the connection. So you will see also that, here that the persistent mode, hey, you maintain only 1 connection. It's very efficient in terms of memory consumption. It's also very efficient in terms of delay, isn't it? Very good. I see you guys. Wow, very good with the sort of problem that is arithmetic nature. Okay, Vincent. Okay. Okay, a cheer from your teammate. Great. All right, and I think we've seen enough. This one is straightforward. Polly will come back to check on all your solutions later. Good. And let's move on. Let's move on. So we talk about the communication model. We've created the socket. Oh, guys, you know what? Maybe I should take on the questions on the live chat. So Yixin was asking, why is it essential to tell base and objects apart? Okay. Yixin, I don't know if you have implemented your own web pages yet. Okay. If you are implementing your own web page in a way that you use tools such as AI, then you don't really know what's in a web page. Okay. If there's a chance, Polly can show you you know what? I can probably do that here. Show the source code. Oh, okay. Yeah. Yixin, click the development tools here. It should be able to allow you to examine the exact HTML file, okay, behind the course page here. And so when you ask for the course page, you are actually asking the base object, that's the home.ntu.edu something, the whole URL. Okay, and if you did not specify the file name, okay, if you did not give the third part, web server will assume that it will be the file that's called index.html. Okay, so that is the base HTML. So every time you click on a link, it asks for the base HTML. But what happened in the base HTML is that there could be pictures or sound that you actually you embed in the base HTML file, but it's actually a file. That picture is a file from somewhere else on the server. Okay, so if you examine the course pages HTML, you'll find that golfer here is a picture at a different location or on the same location as the index.html, but it's a different file. If you download just the HTML, it's just the text. Okay, but to show golfer there on your browser, your browser needs to fetch the image picture, the image file next. So that's the reference objects. So fetching of the base HTML and the reference objects appears that it happens at the same time to you as users, but in the back, it's base HTML first. Your browser, as a HTML interpreter, recalling the video how you said that the client is a HTTP client. It's also a HTML file interpreter. It interprets the HTML file and render a page nice and pretty. So there's some conversion going on your computer, all right? And the reference object needs to be fetched before golfer's picture can be rendered. Okay, so getting the base HTML does not mean that you get everything you need to render the page. There's more. I hope that explains the differences between the base object and the reference objects. Okay, and I think you meant the objects by the reference objects. So my interpretation of your questions will be based on the context, and because you guys are still learning the context, of course you'll be using terms that you're not quite sure if it's correct, which is okay, because learning is a process of gradually figuring out what is right and what is misconception. So I wouldn't call you guys being wrong about something being wrong. It's just misconception because you just don't know the thing yet. Okay, so Ray has a question. When using a pipelining approach, the client is supposed to send requests spaced by the transmission time. Yes, but how does the client know how long it should wait between sending each request? Very good question, Ray. Imagine this. Okay, as a HTML interpreter, once you get the base, you will see there are 5 objects you need to fetch next, right? From the client end, also the browser, also an HTTP client, can then fetch the first one until we get the first one before asking for the second one. Okay, if this is I think this is easy to program in the persistent, even in the persistent mode with pipelining, right? If you have 5 parallel connections or 5 threads, then it gets a little bit tricky. So Ray, you do want to sort of I think you might still be able to send the requests back to back, and somehow the socket will find a way to send them out gradually. But I'm actually not quite sure. Okay, there might be some memory issues. I haven't done that before. So Ray, you can actually see if you can do a threaded program, okay, and do the pipelining part and asking for the 5 reference objects at the same time. Okay, that would be very interesting. Okay, so this is how you can do this is after you see the 5 reference objects, you fork 5 processes and asking for the 5 objects immediately. And see how the page will turn out. Okay, I'll be curious. But using the same connection. All right, I'll be curious. Good. I hope that I addressed the questions. If there's anything not clear, just ask again. And keep in mind, after the Wednesday session, we do have a default office hour. Okay, Polly would be there on the Google Meet session. But in case Polly forgot, just let me know. Okay, by pinging me from Discord or other ways like sending me emails. Good. Hey, let's move on. We know the communication model. We can now establish the TCP connection and start sending messages. And in fact, in the videos earlier, you hear, oh, it's simple, right? The client sends a request message and the server sends back a response message. So the next set of videos is to tell you the request message format, the response message format, and they are also very straightforward. Okay, you'll be surprised. Hey, a web transfer we're using like pretty much all the time. It's so simple. And to start introducing the request message, let me show you an example of how the request message reads. Really, seriously, really. It's only 1.5 minutes. A request message, very straightforward. You have a request line and then a bunch of these header lines. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, okay, keep alive also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP request. Yeah, and you probably guessed already, right? The request line is the exact command you are asking the server for because you see the URL there. Okay, so get this object. So all those header lines, if you pay attention, it seems more like some additional informations for the client to communicate with the servers. That's right. And next video, finally, you will see the format, the general format, more closely. And towards the end of the video, you will see probably introducing a couple more header line comments or methods, okay, that we see very often. Next, the general format. Okay, now with that introduction, with a specific example of HTTP request, this will be slightly easier. You see here, first is the request line. And then we get a whole bunch of these header lines, and it ends with what? CRLF. Okay, in fact, at the end of every line, CRLF, okay? And in the request line, we have 3 components: the method, the argument for the method, and the version. Okay? Some comments might not contain the second component, all right? And you see here, for each header line, we see what? Pair of attribute name and value. So In the slide, we see this is the header field name. So those attributes are sometimes also called the fields, the field names. So attribute value or field name value. Good. So lots of these. Okay. And hey, this is the thing that we did not see in the previous example. Yeah. Occasionally, you do need to have a body in the HTTP request message. And this is what, if you recall, the post command. We're sometimes posting content, posting data onto the server. So those data, those information to be communicated from the client and to be registered at the server will be here in the entity body. So real data generated by the user is here. Okay. So officially, in general form, the HTTP request comes in 3 parts: request line, header lines, and body. But for most of the HTTP requests, there are just 2 parts: the request line and the header lines. Now, let me add a little bit more. First, the post method. You've heard me. There are sometimes web pages that you need to fill forms, okay? Input names, usernames, potential passwords. Okay, those input are uploaded to the server in the entity body. There's another way of doing that recently. Okay? It's called the URL method instead of the post method. What you do there is, hey, you could be clicking just buttons, okay? A certain link, in fact. What the browser does there behind the scene is more like this, okay? Requesting to the server, all right, okay? But it's actually sending a phrase like this. Instead of a file name with a path, okay? So instead of having a path, something, and then something.html. So it's a very weird form of HTTP request. Okay, while we know this is more classical, but these days we see this more. Okay, animal search question mark and then something and something. Okay, so this is actually a query. Okay. Unlike request, request sounds more like requesting for a service, requesting for a file, for an object. But clients often query the server for a service. Okay, for example, look up a database. Exactly. So in a way, the World Wide Web is evolving from a huge hard disk, a global distributed hard disk, to a global distributed database. Okay, so in the HTTP request there, we are actually sending a query. This is the name of the query. And this is the input to the query. So this query obviously contains two arguments in order to execute, for the server to execute. All right. It's using the get method instead of the post method earlier. So this type of a service request is using the get method, but in HTTP request message. And the input is exactly in the URL field in the request line. Okay, and it's this way. Yeah, the query name and then the arguments for the query. All right. All right, so that's the request format. And you can imagine, right, seeing the post command, right? It's the command, it's the method that you can upload the file. Yeah, sometimes you access a website and you upload the file. So in that case, your request message there, the third part, the data part, will contain bytes, definitely. All right, so the last video is short. It's only about 3 minutes. This is to give you a rough idea that the set of methods are also expanding over the years. Okay, so in the older time, HTTP 1.0, the set of methods allowed is limited. Okay, so let's check out the all sets of methods. And the last slide about HTTP requests here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. Okay. But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, what is the version of the web server program you're running over there? What is your IP address? What is the time date? What is the time date, the object that the client is asking for being modified last? Okay, things like that, the essentials about the server, about the object, so that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly differently. And put here, this one is actually quite forward, just to upload the file in the entity body of the HTTP request to the server, right? So in that request, we also specify which path in the server we want to upload this file to. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request. All right, so we're done with our request message. Response message is not more difficult, but you know what? It's time to take a break. And after the break, we'll work on quiz number 10. So this is just to make sure that you are more familiar with the packet formats, okay, or message formats. So it's now 11:12. Let's resume the lecture 11:22. Hey guys, yeah, it's 11:22, so let's resume the lecture and we'll start from quiz number 10. And let's go to the whiteboard mode. Okay, good. Interesting. Okay, 1 second, guys. I know how to fix this issue. There we go. All right, so the ASCII characters, okay, of within the HTTP requests are actually visible, okay, if we just capture the traffic, okay, going between the client and server. So here's an example of an HTTP request message, okay. So you see that this is the method line, right? The request line. And we have a bunch of these header lines. Good. So given a message like this, can you answer Q1? What is the URL of the document requested by this message? And more importantly, tell me why you think so. Q2, is it a non-persistent or a persistent connection, okay, being requested? The client actually seek to establish a connection, okay. From the header lines, you can the server can tell whether the client is requesting for a persistent or non-persistent, persistent or non-persistent connection, okay. And how do you tell? Or you guess how the server tell. All right, good. So that's straightforward. Therefore, we go on to the score. And this is W4 quiz 10. All right, so the question is already there. Guys, how about 2 minutes? I think it's quite straightforward. All right, let's see. Okay, you have 2 minutes and let's start counting time. Okay. All right, great. Even for a straightforward quiz like this, you can see people discover things and look at things from different perspectives. So let's see, Katie here says we can combine the host name and the get request line to form the URL, right? So we definitely see the path and the file name, right? But we did not see the host name. But Katie combined the host name, okay, here. Okay, good. So we get the full URL. Q2 asks, how do you know if the connection is persistent? And so the hint for Katie is keep alive. Yeah, so hey, we said that the difference between non-persistent and persistent is that in the persistent connection mode, we keep the TCP alive without terminating it. Okay, good call, good call. And Ellen here says, oh, Ellen, you modified your answer to Q1, which is fine, which is fine. And this is because you recall URL has three components, right? There's host name, the path, and the file name. Yeah, this is definitely more complete. And oh, you see this, the reason that you think this is a persistent HTTP session is because, it's HTTP 1.1. Yeah, we know that in HTTP 1.1, default is persistent, okay? And the version of persistent connection with pipelining. Very good. All right, keep alive. Very good. Wonderful. Yeah, I guess it's probably very straightforward. Some of you say, hey, I tell it's persistent connection because whether the client specifically asking or not, this is HTTP 1.1 and the default is a persistent connection. All right. Yeah, Yuchi is very supportive. Okay, I love that. Love that. It's always great working interactive group, supporting group. Okay, very good, guys. Not that hard, right? The request message, straightforward. And if you look closer, because it's in ASCII code, you figure out what the client is asking for. You figure out also how the server potentially interpret the message. So humans are intelligent, I have to say. Good. And you know what? I know that you guys will get this right, okay? So Polly will come back to check on your answers after the class. And let's move on to check out the other message, the response message. And I guess that you guys are confident now learning the response message. You figure that it's probably similar. 3 parts, right? There's a special line at the top, and that is called the status line in response message. And again, a bunch of header lines. That is for the server to tell the client a little bit more about itself. And very often the data part will contain real data. For example, if you are asking a web page, then in the response message, yeah, there will be the web page, but in plain text, in ASCII, okay, plain text. So this is the first video, and this video is long because of course we need some time to introduce the message format. And in the well, you know what, it's just long because it's a little bit more complicated than the request message. 6 minutes, sorry guys, it's a bit long. Now finally, the HTTP response message. Okay, the second type of messages in defining the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Some more related to the server, some more related to the object being requested. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates OK, meaning the HTTP server is working well and the object you're looking for has been found. And it's going to come here in the body entity. Now, second part, the header lines, we see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I say that it's actually rising. So I think maybe in just a couple months, there will be more Nginx server than Apache servers. Last modified. Yeah, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's a really long time ago. All right, ep8. What is this? This is actually, hey, for each version, okay, of the object that you are downloading, there comes also with a version number. So ep8 there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. If there are multiple users there using different web browsers trying to upload the file, for example, poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break time, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. Okay, so server there can actually tell the client, you know what, I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially, instead of using the head command, using the real get command, and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right, so if it's more than 100, then you will force close. The server will force close the connection. Okay. So connection, keep alive. Content type, yeah, just like the client-side header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file, and it's coded in ISO AA59. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages. All right, so in this example, you also see that, hey, we leave the TCP connection for a persistent HTTP connection, but for how long? And we send multiple requests back to back, okay? And we allow multiple requests back to back, but for how many? Okay, so you see in this example, the server tells the client, and this is how I'm gonna manage my TCP connection. Interesting, isn't it? All right, before we go on to quiz 11, I have just a short video to share. That is to tell you a little bit more about the status code. And here you see a few more commonly seen status code. Next is just to share a bit more. HTTP response message status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means, ooh, your HTTP request format is not quite correct. Bad request. 404, that means the object you're asking for is not found. 505, HTTP version not supported. So in case you're using a very, very, very old browser, or if you're contacting a server that's very, very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 5. Yeah. All right, and that takes us to quiz 11. Okay, I think the screen capture should be still working. There we go. Okay, hey, you see another message, and this time it's a reply. It's a response message. And you see, status line and bunch of header lines. And then the blank line. Oh, you know what these, right? So if we are requesting a web object, then this is the beginning of the web object we request. Good, so Polly is asking this. Q1, was the document found, right? So this corresponds to the request message in quiz 10. Was the document found successfully? I did not ask you how do you tell this time because it's very, very obvious, okay? So Q2, how many bytes are there in the document? This again, after going through the example in the video, it should be clear. What are the first 5 characters of the document that's returned? All right, so that's all. Quiz 11. Let's go to the score space. W4 quiz 11. Guys, this time also just 2 minutes. Okay, let's start counting time. All right, let's see. All right, Sparrow, you're the first. Okay, very good. Let's see. Yeah, yes. And 3874. There you go. Okay, and the first 5 characters you see from the web object. Yeah, it is less than exclamation sign. Yeah, and DOC. Very good, guys. All right, and this one is so straightforward. Okay, let's not spend more time going over the solutions in the class. And let's move on to the next. Okay, now you know HTTP very well. And let Polly demonstrate how we can be a human web browser. Okay, because the messages we actually send, the request messages and reply messages, are indeed in ASCII text, right? When you type things up, it shows as ASCII text. Okay, so the first video of the demo is just to give you the setup. Okay. So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80 where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application, just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. All right, so Telnet is very, very old. Many operating systems probably doesn't support it anymore, but I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we Telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the Telnet here is a HTTP 1.1 client, and host gaia.cs.umass.edu. Right, so header line. So essentially, we are trying to do a human web browser, okay, by typing online right here an HTTP request message. So once we are done with this, we hit return, okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the Telnet program. All right, so let's switch to the demo mode. All right, so the real demo. This one is a little long, 3 minutes. All right, let's Telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh wow, that's pretty long. The path and file, pretty long. Let's copy it from the sides. And over here and print. All right. And then host poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. This is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw. and an empty line, and then return again. The whole message gets out to the web server at gaia.cs.umass.edu, and the web server returns this http/11 to the 200, okay. And header lines, number 1, the date. Header line number 2, the server. Oh, it's an Apache server. And X power by PHP, I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. Good. And I think let me just go back a little bit here. You see it here. 200 is a very classic example of, hey, the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics, and syntax of HTTP. All right, so finally, fully done with HTTP. So starting from this point and on, so what we'll be giving our additional mechanisms, okay, to enhance, okay, so for additional functions, okay. So first one is called cookie. So if you recall, HTTP is stateless, okay. In certain use of web downloading, it would be nice if the server knows a little bit more about you. It provides certain convenience. Okay, so that is the cookie. That is what the cookie is for. The second is called caching. Okay, and there are two kinds of caching as you see from the topics. So caching is there to enhance the performance, reduce the response time, and lower the traffic required to download the web object. So let's start from the cookie. Okay, so first video is to give you an overview. I mean, the first part can be a little bit confusing because Polly will start by introducing the 4 components, okay, in order to enable this cookie function. And the second, on the same slide, Polly will say why we need cookie, okay. And later in the video, you will see a full example, step by step, and that will make things clear. Okay, so mechanism of cookie. Next, cookies. Yeah. Many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate, okay, a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting of the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay. So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, okay, that arriving at the server, the site will then create a unique ID, okay, and that will be an entry being added to the backend database, right? So that ID is going to be carried, okay, in the message the site sends back to Susan. So that's going to be set cookie and then the number created here, all right? So local hard disk you have there, or Susan has there, will have that entry, okay, set up in the cookie file. So this will go back to the server, okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, okay, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Okay. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID ep8. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website, Amazon.com, the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines, all right? So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID, okay, for this particular user, okay, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. Okay? And hey, see, the ID created is carried over through the HTTP response message back to the user. So, web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am a user 167A header line, right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content, okay? Server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item, okay? And then recommend potentially items you'll be interested, okay? So that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you're looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, okay, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's going to by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there. All right, so that's the basic mechanism. As you see, it's straightforward. Essentially, that's how the server sets some information on your local disk so that the next time you visit the server knows more about you. All right, and some of you might be feeling, oh, okay, that is a little bit freaky. You know what? Yes, using cookie, there's a trade-off from the user's perspective. There's another trade-off from the server's perspective as well. Okay, so let's check out this video talking about the trade-offs. Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, The cookies, from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that. Right? So convenience. But on the downside, those websites would be able to learn a lot about you. Okay, so you store emails. That's pretty much your personal life. You store your purchases there. That's pretty much also your personal life. Okay, so over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell of a lot about you. That's why people are freaked out so much about these big sites. Okay, allowing them to set up cookies, allowing them to store information about you. Okay, so downside, privacy. Okay. Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay, no storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here, you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed in the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states. All right, so guys, you see, there's a trade-off, right? It's convenient sometimes, but in the meantime, the server knows more about you, right? There's a privacy concern. And there's also a technical issue towards the end. You hear that to maintain such that the states between the server and the client, in case it's consistent, there's no problem. But in case, for example, you reinstalled your computer and the cache is gone, then you might have an issue. Or the cache is manipulated somehow, and there's an inconsistency between the client and server. Okay, so there's an additional technical issue. And guys, I would like to draw your attention to the live chat. Polly had a pop-up quiz here. All right, so the question there is, between stateless versus stateful, which mode do you prefer connecting to your favorite shopping websites? So that is also a little bit that's asking this as well. I mean, we go to these websites very often, right? These days, there's some pop-up box that will show up. Do you agree to allow the website to install caches on your computer? Okay, so do you say yes or no? Okay, would you prefer stateless or stateful access, okay, to the websites? And particularly in my pop-up quiz, to the shopping websites and your favorite shopping websites. Okay, guys, go. I see Yu Zheng saying something already. Stay less, because once I browse a certain thing, for example, phone game, it will consistently show me things related to them. Okay. Yeah, it's a little bit freaky. Yes, I know. They know what you want. Okay. Katie says, stay full. For my favorite shopping websites that I frequent, yeah, I would like my recommendations to be customized based on, oh, nice. Yeah. Be willing to give up some privacy for this. And for the websites, you feel that you've been on there for some time, maybe years, and there's no leaking of your, purchasing preferences. Okay, you do not get strange emails that is actually advertising things related to what you are searching for on these shopping websites. Then you feel safe. Okay, working with these websites, right? Let's see what your opinions are. Ting Qi says, stay full. So you are comfortable. And Han Yu Sparrow, stay less. Okay. But Han Yu, because you don't shop often, so there's no such thing as convenience. I see. Ethan, stay less. Qianru, stay full. Easier to find things you want. Ray, stay full. Dorothy, stay full. I would like to remember my preference. Sorry, it's a little bit hard to scroll with you guys entering your input. So Dorothy, we've already seen that. Ellen, I prefer stay full for the convenience. Yeah, who am I asking, right? College students, you probably care less about privacy because people probably are less interested in you. Okay, stay full. Ivan, yeah. Wait, Jordan, stay less. Okay. Oh wow, Jordan, very interesting. Likewise, Polly is also the one who prefers looking for her own solution. Stay full. Lloyd, stay full. Did I miss something here? Yeah, and Andrew, stay full. Stay less, Xingyuan. That's very interesting. Yeah, with the recommendations. I don't know if you guys, because I ask you for the shopping websites. If you go to YouTube and watch videos on a regular basis for your leisure time, eventually you might find that, hey, all these things that the YouTube recommended are boring. And why? They keep recommending things that you've asked for previously. But for leisure, sometimes you will really prefer something new and different. Yeah, stay less. Interesting. Stay full, and finally stay less. I think it's a bit about 3-1 or maybe 5-1. Okay, stay less for Bob. Advertisements flooding. Stay full. You know what, guys? There's also a trade-off whether you do stay full or stay less, right? And human beings is complicated. You can also be, sometimes you prefer stay full, sometimes you prefer stay less. All right, very good to know. I see students who are more considerate towards the end saying stay less. Maybe, yeah, stay less. It's okay. I'll do my search. All right, interesting. So that's Cookie. convenience and privacy. And there's also a little bit of challenge doing the implementation. Next is going for the performance, particularly the response time. And doing caching sometimes helps reducing the amount of traffic consumed to download the web objects. And the easier one is called local cache. And the saving is not much. You will see. This video, almost 3 minutes. The next two topics are more about trying to reduce traffic between the server and the client, or trying to reduce the delay downloading a certain object. It's called the caching. So what cache means is to store a temporary copy of certain data. Okay. So conditional get here is like to have a local cache of the web pages that we have downloaded previously. Okay. So the goal is to not send the object again and again and again if the copy we're storing here is already the latest. Okay. Because as a result, we don't need to send the object, and that reduces the delay, and we also reduce the bandwidth requirement. Okay. And so saving the bandwidth is going to be good for everybody. So the way it works is this. Okay. So the first time the client downloads a web page, it's going to keep the copy of the web page on a local cache. So that's somewhere in your local disk. And in the meantime, we record the date, okay, the cache copy is downloaded. And so that when we send a request for the same page again, we carry this special line in the header field, the if modify since, and then the date, okay, of the cached copy, the day we have requested the copy the first time. And then at the receiver side, at the server side, the response will contain the no object if the cached copy is actually the most up-to-date, meaning if the copy at the server has not been changed after the date, then there's really no need to send it again back to the client, okay, because the copy right here is already the latest. So in that case, a special HTTP response message is going to be sent, and the status line is going to read like this. Yeah, 304 not modified. And in the body of the HTTP response message, it's going to be empty. Okay, so no need to send the object. And the way it works is more like this. Let me illustrate. The second time, the client here requesting for the web object sends request message and having this in the header line. If modify since the date the page was downloaded the previous time. And if the server finds that no, it's not yet modified, then send back a short HTTP response carrying the status line. And that's all. No data here. But otherwise, if the object is modified, then we send back a regular HTTP response that says 200 OK in the status line and the web object, the web page again, okay, in the body and the T. All right, so that's the local cache. And by the way, the if modify since is not checked every time you request, okay, a web page. And that's why sometimes you feel that you have already updated your web page. But if you go check on your web browser, it remains the same. Because you have a local cache of your page. And very often you need to reload, okay, a number of times in order to see how, or wait until a later time to see it shows. Okay, so it really depends on the setting of your browser, and sometimes depends on the setting of the server. Sometimes you get a cookie from the server that you do the if modify since every now and then, things like that. Okay, so that's local cache, and it's a perfect time to take a break. I mean, for the class today. And next week, we'll start by covering web cache. So this thing is more interesting. And the saving in terms of response time and traffic, download traffic will be more significant. All right, so I will see you next week, and we start from web cache. And thank you for your participation. Bye, guys. All right. All right. Happiest time of the day. Yeah. Yay, done. Bye.